All right, so good afternoon again, and trust you had a good week. And today I would like to talk about surface creation and analysis. In fact, I want you to understand how surfaces are represented. Then we will go to the software. So those whose software are still not fixed, maybe you can be listening aloud whilst you finalize it. Okay, the name of the software is QGIS. So I mean, even in 2 minutes, if you know what you're doing, you can just fix it. But till then, I want to touch on surfaces. I want you to appreciate what surfaces are too in GIS. Are you okay? We need to appreciate that surfaces represent phenomenon. Can you see everything on my screen? What can you see? Surface creation analysis.
So it's your picture that we are seeing.
Oh, sorry about that. Okay, so you should be seeing Chrome now. Okay, great. So you see surface creation analysis now.
Yes, sir.
Okay, great. So this is very important to know because there's a whole lot of analysis that are done that are not necessarily vector-based, and that's why I need to touch on this. Also, some analysis are done which are also raster-based, but then they all kind of relate to what we call the surface. All right, so surfaces represent phenomena that have values at every point across their extent. What does that mean? That means that the thing that what we call a surface, like the road surface, is not, you can look at it a bit, deeper than that in terms of data. Are you okay? So values are data. Are you okay? Are coming from data. So when you look at a surface, then it's like as if every single point on the surface has a certain value. Are you okay? So you can have a tarred surface. So every part of it that is tarred, yeah, in a continuous kind of region, with similar attributes, values. Are you okay? All right. Now I say that the values are the infinite number of points across the surface are derived from a limited set of sample values. In other words, the surface that you create are actually from sample value. In this case, it's talking about surfaces as represented in the computer, not on the ground. Are you okay? Which means that how do we represent the surface for our project in the computer? We will have to take sample values because we cannot visit every point on the surface because every surface contain an infinite number of points. Are you okay? As is being specified over here, an infinite number of points. So let's look at water surface. You realize that there's a whole, you can't even tell exactly where it breaks. It's continuous. As long as there's water, then that surface is totally covered with it. And you can't count them. There are millions of points that make up that surface. Are you okay? As opposed to what? As opposed to trees that have been planted between one tree and the other, there's space. So that's where a surface. Those things are what actually point locations with certain things. Are you okay? Certain objects, certain phenomena. Are you okay? Or things. Are you okay? All right. Now, the sample values may be based on direct measurements such as height values for an elevation surface or temperature values for a temperature surface. So now here, elevation surface and temperature values for temperature surface. Are you okay? So what does that mean? It means elevation surface means that if there's no elevation, you cannot be walking from one point to the other. Because we immediately realize that there's no height there. You are dropping into a bottomless pit. I think I've said this before in the raster data model. Are you okay? All right. So it's very important that we actually know this, that a surface is not, we just can't use the word surface as an engineer or as a scientist and not look deeper into what goes into it. They have values. A surface is really made up of values. Are you okay? And they are infinite, at infinite points. Are you okay? All right. Now, another way to actually extend and to create more values between the sample values is to use what we call interpolation. I believe you all made that word before. In other words, you are trying to find the unknown value between two known values. Are you okay? So that is what happens with surveyors going to pick spot height and then architects asking for those spot heights, and then trying to interpret what those spot heights are, and say that, okay, then it means we are sloping this way, and so I need to have, okay, my building on the other side of it, and stuff like that. Where should I have the landscape going? Are you okay? We need to appreciate it. Are you okay? So it's important to know that we can actually derive surfaces from other data. Is that okay? All right. Now, surfaces relate to what we call slope and aspects. So now slope, I think we all know what slope is, right? It's a change in elevation, change in height between one point and the other, the rate of change. Are you okay? And the aspect has got to do with the direction of the slope. So I think we touch a little bit more on that. So slope is the rate of change, and then the aspect is direction. For now, take it like that. So in which direction is the slope from Malam Junction to McCarthy Hill? As you go up the hill, what is the direction in which the slope is facing? That kind of thing is what we mean by aspects. Okay, so aspect, surface. Okay, so there are different types of surfaces. The temperature surface will be made up of values of temperature, and everywhere you are on the earth, there is a certain temperature. It may not be what you want. It may be too hot or too cold, but there is a value for temperature. It may be just normal and okay for you to live in it, and maybe too hot to just destroy you. But basically, that is that for a temperature surface. Are you okay? We also have a surface of distance from bus stops in a city. Is that okay? So we have what we call cost distance. In other words, if I have a surface in which I can tell how much it will cost me or how far I am from a certain point, that is also a type of surface. Okay, all right. So now some of these things are used in suitability analysis. If you want to find out if it's suitable to say have a what do you call it, a dump where you dump refuse. What's the popular name for that in civil engineering? Where you dump refuse. Anybody's mic is on. Where you normally take all AMA, the city authority takes all the refuse and dump it. It's called what?
Is it dump site?
Yeah, exactly. Dump site. I think there are other alternate names for it. But yes, you can call it dump site. But it's actually a particular location where all the trucks take all the trash, put them in there. Are you okay? All right.
Okay.
Okay. Landfill. I think we've heard of
landfill site.
Landfill site as well. Okay. So now we can also have surfaces showing concentration of criminal activity. We may not be interested in that as civil engineers per se, but I want you to appreciate the fact that the word surface is not just the way you see it. It could be more than that. Are you okay? You could be looking at something more. All right. Now these are examples. So surfaces can be represented using contour or isolines, arrays of points, tins and rasters. I talked about tin, triangulated irregular network. Is that okay? Rasters. So in that case, squares. Think about regular gray squares. Remember we talked about raster model. Okay. But we are saying that most surface analysis in GIS is done on the raster or the tin data. Now remember, the tin is the one that I told you that most cartoons that we're watching on TV, these days you watch cartoon and you can't determine the difference between the cartoon and reality. You're watching a movie which is 3D, totally animated. Are you okay? And yet you can't even figure out, am I watching cartoons or I'm watching a real thing? And that's coming from these triangulated irregular networks. Are you okay? So the perception is created. Perception is created that you're actually looking at something solid. Okay? So rasters are very, very crucial in GIS. Most analysis in GIS on surfaces are done using raster. Okay, but then let's look at contours. Contours, we all know, I don't know if we all know it, but if you don't know it, they are lines that go through points of equal height. Are you okay? All right. So there are sets of lines of equal value across a surface, but we talk about equal height at junior high school. All right. They are frequently created to create surfaces on a map. Are you okay? Points. We can use points. So hotspots. I don't know. I'm talking about this one. Spot heights, not hotspots. Spot heights. Okay. So the spot heights are what you find on the map. Normally you see plus 75. That means that like the height there is 75 above a datum, okay, which you need to appreciate. All right, so here we go. They are usually used as inputs to interpolation. Okay, I'm using this laptop which has too many notifications popping up. Okay, so we can use the spot height to create a new surface. Okay, and so through interpolation or through what we call kriging. So I'm not talking about kriging here. You know, in another lecture we'll talk about that, but not in this one. Okay, triangulation tools to create raster or thin surfaces. So thin surfaces, raster surfaces, this are actually made up of squares. Every square contains the height, okay, in a value, and the value could be height. Okay, it could be height, or it could be temperature, or whatever else. It could be soil acidity, could be soil type, or moisture content. If you were actually doing some really, extreme case of a road, and maybe moisture content variation meant a lot to the design. Are you okay? So we actually use points to generate surfaces. The points themselves can be interpreted. I can look at a set of points with high values and quickly tell you what is happening. That maybe water is likely to be flowing that way. But we could start with points. Okay. So tins, I think we already talked about tins, that they are triangular facets, and they are defined by nodes and edges. I told you edges are like links in networks, yeah, or they are lines, really. The nodes are points, the beginning and end, the node or the arc. All right, so things are constructed from, I think how things work, we've already touched on that, and there'll be no need to really go over it again. So things are constructed from a set of known values, sometimes called spot heights, but actually spot heights are really popular for that. Okay, so there you go, rasters. Let's look at rasters. So rasters are used in GIS for most of the surface analysis. Rasters are rectangular arrays of cells. Okay, I think we know what rasters are. Do I even have to go over it again? But once you talk about surfaces, then we should realize that every project area can be tessellated. I'm saying this again, this is like a repetition. Sometimes when you're lecturing, you do a repetition of something already said. You take a project area, cover it up with squares, are you okay, via some kind of grid, base system, like a camera or a sensor mounted on the platform, like an airplane or helicopter or a satellite, which has been launched into the skies. And then you get the rectangular array of cells. So this is why we're talking about rectangular array of cells. It's the reality is some kind of camera. Say, if you could actually take your phone and mount it under an airplane, practically don't do that. But if you actually did that and took a picture whilst the plane is in the sky, everything you got is really a rectangular array of cells, of the given area. Okay, so here we are explaining how rasters work. I think it's a double explanation for you. A given cell contains a single value, so the amount of detail that can be measured represented for the surface is limited to the size of the raster cells. So gentlemen, take note of the size of the raster cells. It's coming to you for the second time. So this is the second coming of the raster cell. The size of it is also related to what we call the resolution. And I told you that the resolution is what people pay a lot for when they buy their phones, the cameras in them, the cameras in their phones. Okay. All right. So I'm touching on surfaces in this presentation. People like calling around. Okay, it's my dad again. I told him that I'll be doing a lecture today. All right, can you hear me? Or are you still there? Okay, so we can do. Hello, are you there?
Yes, sir.
So please,
Okay.
sir, come back with the size of the resolutions, please.
Okay,
the line went off, so we didn't hear
that's
it.
Fine. That's fine. I'm okay with that. Okay, so we said that. Excuse me. A given cell contains a single value. Okay. Remember when I drew that, those squares to explain the raster model. Okay. So the amount of detail that can be represented for the surface is limited to the size of the raster cells, the amount of detail. So what it means is that the size, when you divide an area into squares, I wish I had my board again here. Let me go to annotation and see if I can do something. Let me get lines. Draw
Okay.
lines, yes. Okay, first the square. Okay, so if I have, a set of squares, so this like, do my best to do it. Okay, so let's say I have 3. So these are 3 cells. Okay, I'm not really doing it very accurately. Okay, so if I want to represent something using these squares, let's assume these are really squares. They are not. Okay, and I shouldn't even be trying this. It's precarious. But obviously, if these were regular squares, this is my zoom, squares. Forgive me for that. So if I divide an area into this number of squares, then obviously, if I'm going to be recording a value per cell, okay, one single value per cell. Think about a temperature surface. The smaller the squares, the more detail I can get, the more variation I will have. Did you follow it?
Okay.
The temperature for the whole Ghana can be represented as 1 on CNN or BBC. Do you agree on that? What that means is that there's a falsehood in that, isn't it? Ghana, there's only one temperature in Ghana. Temperatures vary, right? Okay, but
Yes.
it seems as if when CNN gives us one temperature value for Accra, Ghana, what they've done is that they've blocked the whole Ghana as one square, one cell. Now that cell can be divided into thousands. Then we'll be getting different temperatures varying from northern region to southern Ghana. So the size of the raster cells actually tell of the amount of detail, are you okay? That can be represented. Do you cannot get it somehow? So think about the amount of detail as, remember that this whole lecture, GIS is about representing what? Modeling our world. Are you okay? Think about it. Every engineers, that's what we do. Is that not true? Don't we model first, then we design, isn't it? So that's what GIS is doing. You are trying to actually model. You are trying to get, so in the surfaces, when we talk about surfaces, remember, we are trying to represent surfaces. That is what, so in this lecture, you should be thinking about it. What I'm trying to do is to tell you how we can represent a surface in the computer. Are you good? All right. So the size of the square means that we are only having a single value because every square contains a single value, right? Up here, a single value, okay, contains one cell, yeah, single value in one cell. So the more cells you have, you'll be having a lot, isn't it? Right. So the size of the raster cells will also determine the amount of detail you can have. In other words, for a particular area, if the squares are getting smaller, the cells are getting smaller in size, that means you're having a lot of them. And if the cells are getting bigger, then you're getting smaller amount of them. And I even use the megapixel on your phone. All of you, as an experiment after the lecture, go take your phone, check the megapixel you have. It means that those are the number of millions of squares that you have on your camera when you are taking a picture. And it will also directly relate to the amount of money you paid for your phone. Normally it goes with it. Are you okay? So sometimes that's why people don't like their phone. They say, give me they have phones, but they'll take your phone to take a pic because the number of squares, cells are small, are very large for them. And then for you, you have a lot of them. And the quantity, or it can be quantified by a value called the resolution. Are you okay? All right. So for every imagery, you can associate a certain quality called the resolution. And it links up with the size of the raster cells. Okay. Is it any better for you? Hello? Hello? Whoever asked the question, is it clear to you a bit?
Yes, it's okay.
Yes, sir.
It's okay. Okay. All right, so basically that is that. So raster, data is needed if you want to do surface analysis, a lot of surface analysis. All right, so one of the things that we do during the surface analysis is to do an interpolation. Is that okay? So interpolated values, like I said, are to determine places where there are no values. You try to get values for them. Are you okay? So as you can see in this picture, the value at, excuse me, get my spotlight. The value at this point is 662, okay? And the value here is 564, okay? All right, the value here is 466. And it could be anything. That value can be height, or it could be temperature, it could be soil acidity, it could be soil moisture content. Are you okay? Please pay attention. You need to understand, because the questions that we always asking are a bit tricky. All right, so understand it. So now here, the value here is 184. Okay, all right, the value here is 242. Okay, now I'm not interested in the values on the board. They don't matter to me. I wanted you to appreciate that there are certain values that have been measured at particular places on this surface. All right, now look at the green background. The colors there are not to make it look beautiful. The colors there are actually the raster. That's the raster data that you're looking at. Are you okay? So it's like the points have been overlaid on the raster. Okay, we have 10 minutes.
Okay.
We have 10 minutes. So guys, when it cuts, we go for the previous link. I'll try to finish up with surfaces. I don't want to go deeper than I need to, honestly. But I want you to appreciate the basic. All right, so now what is happening is that the raster data set are being generated from the points, which is actually vector. So the points are vector. Remember that points, lines, polygons are vector, are synonymous with the vector model. And then the squares, regular gray squares, tessellated, are actually what? Raster. Okay, now, so what it really means technically is that if I'm to zoom if I'm to go really, really close,